Hello everyone, it's me, Mr. Younger again. This time I have an example of a center of mass calculation. This is a pretty straightforward one, not unlike the first one that your book has and at the beginning of the or at the beginning of that section in your chapter. But either way, it's just a slight bit different and maybe a little bit more helpful. So let's go ahead and share my screen. All right, so here's our problem. I've got it stated here just in terms of words. I don't think you really need a drawing, but I will be adding a drawing a little bit later just so we can make up a coordinate system because inherent in this formula for this center of mass is basically x coordinates, y coordinates, z coordinates, and therefore in each problem you have to sort of establish a x, y, z coordinate system. Or if it's just one dimensional like this one, you can just start at x-axis with an origin. Therefore, you might as well draw a y-axis too, but at least a zero on a number line. So, anyways, we do need a coordinate system, and I'm going to show you that in the next couple of slides. But here's the problem: three children are sitting at various locations on a light but strong plank that is 4 meters long. The first child has a mass of 45.3 kilograms and sits zero point zero 0.08 or 0.82 meters from the left end of the plank. It's supposed to be a of there. The second is 51.8 kilograms and sits 2.00 meters from the left end. And the third is 63.0 kilograms and sits 0.81 meters from the right end of the plank. A, ignore the mass of the uniform 30 kilogram plank and determine the location of the center of mass of the three-child system. Part B, where along the horizontal plank measured from the left end could the plank be and kids be balanced on a 2 by 4 oriented perpendicular to the plank, but also horizontal? In other words, if the plank was laying this way, if you put a 2 by 4 right here, a 2 by 4 is fairly narrow, so you're basically just asking at what point. Obviously, this gives you a little bit of freedom as long as you're within roughly 3/4 of an inch from the center of mass. It's probably going to balance. So, anyways, to do this, let's go ahead and start off with our solution. So the formula that we'll be using entails the x center of mass. This is essentially a one-dimensional problem, so I've run ahead and written solution. XCM equals m1 x1 plus m2 x2 plus m3 x3, all that divided by m1 plus m2 plus m3. Now I've drawn the first two because the first two statements are pretty straightforward. It said uh, the first child has a mass of 45.3 kilograms and sits 0.82 meters from the left end of the plank, even though it says is the plank. The second is 51.8 kilograms and sits 2 meters from the left end. So I've got these drawn on this diagram, but notice it says and the third child is 63.0 kilograms and sits 0.81 meters from the right end of the plank. You got to watch out for that kind of wording in physics problems every day because they're just looking for different ways to make sure you're paying attention to the actual physical problem and that you understand the wording and that you're just not going too fast. So I decided to stop in the middle of this with just the M1 and M2 drawn with the X1 and X2 drawn. Notice I've also created a coordinate system. Since we were doing everything relative to the left end of the plank, I went ahead and put the y-axis at the left end of the plank and then the x-axis along the plank so that the x1 is just the 0.82, the x2 is 2.00 meters, but to draw the x3, that's a little different. So you see now that I've included M3, which is 63 kilograms. That's actually 0.81 meters to the right, excuse me, to the left of the right end. Our coordinates are set up such that the x zero is at the left end of the plank. So I actually need to figure out how far it is from the left end of the plank to the 0.81 meters from the right end of the plank. So to do that, I know the right end of the plank's at 4 meters, and I just have to subtract 0.81 meters for it to get 3.19. So that's all I've done here is just shown another diagram that includes the 0.81 meters. That includes the 0.81 meters, as well as the first 0.82 and the 2.0 meters, and then the actual value of x3, which is 3.19 meters. Now we can just continue. Now that am ready to do part A, I'm going to go ahead and start off with the formula. In this case, we're ignoring the plank, so we just have the three masses. So the x-center mass is, like I said, m1x1 plus m2x2 plus m3x3 divided by the total mass. Now, I write all the numbers along the bottom. Notice they're all in kilograms. And I started writing the first two terms, and I wanted to include the units so you know what they are. So it's 45.3 kilograms times 0.82 meters. That's going to give you kilogram meters. The bottom's going to be in kilograms, so you can actually divide out the kilograms to get just meters. So the x-center mass should come out in meters like we expect, but I'm not going to take the time to show the kilograms and the meters and the rest of the numerator, so I just chose to do a stop there. So now you can see I've actually added in the additional 0.81, 0.82, or excuse me, the 51.8 times 2, and so on and so forth. I've went ahead and added those now, and still have the same thing here. But you can see now this will be kilograms, meters, kilograms, meters, kilograms, meters, and then divided by kilograms gives us just meters. If you do these calculations, notice the sig figs are only going to give you two sig figs in each of these multiplications, or at least in this first one right here, you're only going to get two sig figs. So when you multiply 0.82 and 45.3, that's literally only going to limit you to two digits and whatever decimal place that's in. Because it's addition in the numerator, that's going to set the least significant digit in the far right side. So you got to keep an eye on that when you're dealing with sig figs. Again, my class, you don't have to worry about sig figs, but just in case you do. So when I calculated all that, what I discovered was basically we were going to have to cancel out the 45.3 times 0.82. Let me double check that. 45.3 times 0.82. That actually gives me 37. Oh, because that's the nearest whole number. So actually, in principle, I could have gotten instead of two sig figs in the numerator, I actually could have gotten three. What I did was looked and realized that some of them wouldn't be three sig figs like the 51.8 times 2 and the 63.8 63.0 times 3.19. Those would be at least three sig figs. But I looked at the whole numerator instead of just that first term. That first term turns out when you multiply 45.3 times 0.82, you get 37.146. So that's actually good to the nearest whole number. So I can go ahead and change this and make it just that the last significant digit is actually the ones place, not the tenths place. So when I do that, I now have three sig figs divided by four sig figs. So that gives me three sig figs. That means the 2.134 meters is actually 2.134 with only the four being non-significant. So again, all I've done is do the mathematics that you see written down here, and then I just computed 341.716 divided by 160.1, and then rounded it to the appropriate three sig figs. Now in part B, they want us to know where along the horizontal plank measured from the left end could the plank and kids be balanced on the two before oriented perpendicular to the plank, but also horizontal. So in this case, that's sort of a way of hiding what you're asking for. You're saying, okay, let's see if the student knows the actual concept of where would you balance a plank with kids on it. Is there a name for that specific location? And yes, that's name is the center of mass. So we're just trying to show you the different ways someone could ask for something without actually explicitly saying center of mass. So in this one, we're doing part B. The formula for part B is now that we have four masses. It's m1x1 plus m2x2 plus m3x3 plus the mass of the plank times this x position of the center of mass of the plank. Now, the plank is a uniformly distributed mass plank, so that means it's basically uniform. Every cubic inch of it weighs about as much as every other cubic inch of it. So what that means is the center of mass should actually be at its geometric center. So if the plank is 4 meters long, then it should be 2 meters long, and that's what we're going to use. So the position of the plank, as you can see in the drawing here, the position of the plank's mass is shown right at the 2.00 mark, which also happens to be where the 51.8 kilogram child is. Now, we can go about calculating it as 45.3 times 0.82, the 51.8 times 2.0, the 63.0 times 3.19, and then we have the mass of the plank times the center mass of the plank distance. So that's 30 times 2, and then we have to divide that by the total mass. This gives us divided by 45.3 plus 51.8 plus 63.0 plus 30.0. And again, in this case, what we've discovered is still on that top, the 3 is actually a significant figure, just to remind you of that. And the 4 is actually a significant figure. And the 1 is also a significant figure here. Sorry about that. It's just a mistake I made in that first one, and it's going to show up every time. But anyways, now we're doing this center of mass for this part B. Again, you're just going to take and multiply the mass times the center of mass distance for each of the parts. It's basically the same calculation we did before, except now we're adding 30 times 2. So if I add 60 to 341.716, I'm going to get 401.716. And in the bottom, it's the same calculation as the bottom of the top, except I'm now adding 30.0 kilograms. So that instead of being 160.1 becomes 190.1. So now, if you take those two numbers, 401.716, again, this 401.716 is actually not supposed to have that as a non-significant figure. That's actually supposed to be a significant figure for the same reason we discussed about a second ago. So again, I apologize for making this mess, but that's also going to give me one extra sig fig here, and that's good. So again, the 401.716 divided by 190.1 gives me 2.113. So you can see it's a difference of about 2 in the last significant figure. Again, remembering that the significant figure in this part A was actually so 2 decimal places. So in this case, we didn't get it to the same number of sig figs. So if we actually wanted to have it the 3 sig figs, or at least to 2 decimal places, we would have been safer by taking into account the mass of the actual plank. But either way, here's the result. And remember, we're actually just calculating the center of mass. So I took time to say, well, technically, X center of mass is 2.113. But as we said, the 2.113 meters is also the balance point. So in other words, if I were to stick my finger out or 2 by 4 out, you could lay that plank right on that thing. And on that particular position of the plank on that finger or 2 by 4, and it would actually balance. So that is our actual final answer for part B, and I hope that helps you understand how to treat and calculate the center of masses for discrete bodies, objects made up of a countable number of objects, or systems made up of a countable number of objects, like 3 kids and a plank or so on. I hope that helps. Have a good day.